So hello everyone, welcome to TAF. I'm Jay, assistant professor in the Web Information System group at TU Delft. Nice to see you again and welcome the new audience. Now, first of all, let me give a brief recap about the topic before introducing today's talk. So human-centered AI studies the design, development, but also the use and governance of AI systems for supporting human activities in trustworthy manner. This speaker series of human-centered AI focus on the knowledge and language aspects, which are key concerns in making AI systems and humans understand each other and acting upon such an understanding through interaction. Now, on these topics, we have invited a list of speakers whose work has made foundational contribution to these fields. This week, I'm thrilled to introduce our speaker, Matthias Boehm, full professor for large-scale data engineering at Technical University of Berlin and the Bifold Research Center. His cross-organizational research group focuses on high-level data science-centric abstractions, as well as systems and tools to execute those tasks in an efficient and scalable manner. From 2018 through 2022, Matthias was a BMK endowed professor for data management at Graz University of Technology, Austria, and a research area manager for data management at the co-located Nantes Center, GmbH. Prior to joining TU Graz in 2018, he was a research staff member at IBM Research, Almaden, California, USA, with a major focus on compilation and runtime techniques for declarative large-scale machine learning in Apache System ML. Matthias received his PhD from Dresden University of Technology, Germany in 2011 with a dissertation on cost-based optimization of integration flows. His previous research also includes system support for time series forecasting, as well as in-memory indexing and query processing. Today, Professor Matthias will introduce the work on system infrastructure for data-centric machine learning pipeline. Now, to all the participants, feel free to ask questions during the talk, but please use the chat during the presentation. Now, after the presentation, you can unmute yourself for questions. Now, without further ado, let's welcome Professor Matthias Boehm. Thanks again, Matthias, for being here. The floor is yours.
Awesome. Thank you so much for the very kind introduction. This naturally leads over to this About Me slide where pretty much you see the same content that was just introduced. So I'm largely focusing with our entire team on building system infrastructure for the end-to-end data science lifecycle, from data integration, cleaning, over efficient distributed training, all the way to model debugging and deployment. So I have to say, as a big disclaimer, I'm by no means an expert on human-centered AI. And however, I assembled a talk that essentially tries to bridge those communities of showing what we are doing on system infrastructure, system internals for distributed machine learning, but then picked essentially two works, prior work of our group, where there is some connection to human-centered AI, and I'm more than happy to dive into the discussions there. So as a start of the talk, we need to talk about what are data-centric ML pipelines, for which we try to build system infrastructure. So at a very basic level, you're probably all familiar with the classical ML pipelines where you have some feature matrix X, some labels, so the response variable Y, and you have some form of iterative training procedure to yield a model. And then you might use that model for scoring and inference and deploy this actually in practice. So at the end, you get something 85% accuracy. Normal ML pipelines kind of wrap those training procedures and scoring primitives into functions and assemble them into a pipeline, often prefaced by some form of data preparation where you get your structured features. If they're categorical, you perform something like one-hot encoding, and you might perform other transformations like binning or word embeddings for text data. Now, data-centric ML pipelines essentially wrap additional outer loops for hyperparameter tuning and model selection, but also things like neural architecture search of finding actual models around those core pipelines. And the key observation for data-centric ML pipelines is then that often the algorithmic details actually do not matter as much as creating high-quality, good coverage datasets by means of data integration and cleaning, but also things like data augmentation, where we take a small label training dataset and synthetically generate examples via reflections, shearing, and other forms of transformations in order to get better coverage over the target domain. Furthermore, those data-centric ML pipelines also include primitives for actual data validation, model debugging, and ultimately kind of deployment techniques into potentially resource-constrained environments. So in our group, we also did some work, and I will talk today a little bit about slice line for model debugging. But then there are additional techniques. So we have prior work on how to parallelize feature transformations in a very effective manner, as well as how to enumerate data cleaning pipelines, which is the second project I want to talk about today. However, in addition to that, data-centric ML pipelines also include means of data engineering. So, for example, in a couple of actual real-world use cases we were involved with in the last couple of years, just aligning multiple modalities. So we have done some work in the automotive space where you get irregular time series from the entire CAN bus system. So in that project, we got like 1,400 irregular time series. You get video feeds left, right, front, rear. You get radar information. You get additional mobile eye event streams from the windshield. Now, often those modalities are misaligned. So if your videos have variable frame rates or some other form of corruption, so the first step before you can train any model is to in a very conscious manner, kind of align those modalities to then feed them into your actual training. Now, what we so there are a couple of observations we can make in this context of data-centric ML pipelines. Number one is that those additional outer loops lead to a hierarchical composition of library functions. And because many of the state-of-the-art algorithms for data engineering, data cleaning, data preparation are themselves based on machine learning, it makes total sense to build those abstractions on top of existing machine learning systems. And that's exactly what I'm going to talk about. Now, in our system, Apache System DS, we essentially provide a domain-specific language with R-like syntax, and then build on top, which we compile into hybrid runtime plans of local and distributed operations. But on top of this domain-specific language, you're building built-in functions for all those different primitives of a data-centric ML pipelines. So this ranges from algorithmic level, and if the syntax is awkward for you, we inherited this %% from the R matrix package. So this is simply a matrix multiply because R uses % to define custom infix operators. So you have some training procedures here for linear regression. You have an iterative algorithm and a closed form direct solve algorithm. And then you can build abstractions on top of that. The key aspect to realize here, our domain-specific language deals with abstract data types of matrices, frames, and implementation-agnostic operations. So this is simply a matrix multiply and does not specify if this is a local or distributed matrix multiply. Similarly, the data object, so this is a matrix, does not force us if this is a dense, sparse, compressed matrix or local or distributed matrix. And also we build those kinds of individual algorithms, but also higher level primitives. Here we see an example for a feature selection algorithm, specifically a feed-forward feature selection, where we take the data set, take the individual features, train individual regression models, look what the most predictive feature is, and then iterate over the remaining features and run what-if analysis. If I would append this additional feature and train regression models, what would be the accuracy, and we terminate if the AIC no longer improves. And what we envision is then the user actually just utilizing those primitives at the highest granularity of those composed primitives, still allowing the optimizing compiler to collapse those abstractions and optimize end-to-end data science pipelines. Now, the system we are building for more than a decade now is Apache SystemDS. SystemDS takes those high-level domain-specific language scripts and go through an optimizing compilation chain of compiling hybrid runtime plans of local and distributed operations. And over the years, we essentially added more and more backends. So when deep learning became more and more important in practice, we added additional GPU backends. And in the last 3 years, just open this up here, in the last 3 years, we also added, for example, a new backend for federated learning and federated linear algebra programs, allowing us to compile all those kinds of data-centric ML primitives and pipelines into federated execution plans as well, allowing us to build models without central data consolidation. So there's a long history of the Apache SystemDS project. It started as a proprietary IBM product, which we then open sourced in 2015. You see here Beth Smith, back in the days, the general manager for software development at IBM, announcing the open sourcing of SystemML at Spark Summit in 2015. I was actually sitting among thousands of people there in the audience. Then it graduated to a top-level project, and when I joined TU Graz as a full professor, we rescoped from just ML training to the end-to-end data science lifecycle, renamed the project to SystemDS, initially as a fork of the main code base of Apache SystemML, and then we're invited to essentially merge everything back into the Apache code line. And since then, it has been renamed to Apache SystemDS, and all the research we are doing in my group is immediately integrated into open source and available to existing users. What we've learned over more than a decade building the system infrastructure is that it yields a protection of investment into the individual primitives and algorithms we are building on top. So for new technology that ultimately always will come along, we don't have to build dedicated libraries for those individual algorithms and primitives, but it yields a separation of concerns to focus on algorithmic aspects at DSL level, and as new technology comes along, add additional backends and only be needing to modify this optimizing compiler, which yields this separation of concerns, which worked out very well. So we've seen it a couple of times when technology moved on from MapReduce to Spark, later to GPUs and federated learning. And this separation is something we strongly believe in, and it was highly successful in the past. Now, in the next couple of slides, I want to show a couple of examples of system internals that we leverage and extend upon in order to eliminate unnecessary redundancy. The first example is sparsity exploiting operator fusion. So in data-centric ML pipelines, we have ultimately DAGs of linear algebra operations, statistical functions, and they create materialized intermediates, so frames or matrices. And in practice, we see ubiquitous fusion potential of, instead of executing operations one by one, merging them together and creating custom operators. So a very simple example is here the sum of x element-wise multiplied y, element-wise multiplied c, where reading from the input matrices, allocating the intermediates, writing to the intermediates, and ultimately summing them up. The allocations or the floating point operations are completely in the noise, and just data movement is the main bottleneck. So collapsing all of that into a single operator that reads the inputs, does not allocate intermediates, and just computes the final sum, largely can improve performance. Similarly, this might be a little bit more complex example, but what it is two vector matrix vector multiplications chained along each other. And if you now realize that this vector intermediate we are creating every cell in there is joined in the second matrix vector multiply against the same row where it originated from, which ultimately allows us to merge this together. Matrix vector multiply is a memory bandwidth bound operation. So instead of scanning X twice, we scan a row, compute the intermediate, immediately scan the row again, and hoping that this row sits somewhere higher in the cache hierarchy. So it looks like we're scanning the entire data set X just once, which yields a 2x performance improvement. Furthermore, there are kind of more hybrid versions where we scan intermediates multiple times, compute multiple aggregates, and similar here, we want to code generate a fused operator that does everything in one shot. And that's what the heading is actually about. We can also utilize sparsity. So this is an example coming from a matrix factorization scenario. Imagine you have users and products. You have a sparse ratings matrix. A user rated a 3-star for a particular product. This ultra sparse matrices often 10 to the -7, 8 in terms of sparsity. Now, what we want to compute is a low-rank factorization that roughly approximates the sparse ratings matrix. But creating this matrix multiply of those factors creates a dense intermediate, plus EPS creates a dense intermediate, log creates a dense intermediate, and ultimately, every 0 in the sparse ratings matrix, element-wise multiply prunes away those unnecessary computations. So what we want to do is fuse this entire operator together, iterate over the non-zeros, compute dot products as necessary, and accumulate in this full sum. So if you do that, and in comparison with TensorFlow XLA, which is also a code generation framework, as well as Julia with dot fusion semantics, on the x-axis, we vary the sparsity from dense to really sparse in 10 to the -4. And on log scale, you see the execution time in milliseconds. On the y-axis, so TensorFlow for dense, pretty good performance, but both Julia and TensorFlow can't really exploit this sparsity yet. And you see by orders of magnitude, you can outperform those kinds of existing systems. So this is avoiding unnecessary materialization and exploiting sparsity across entire chains of operators. The second one is we've been doing work on multi-level lineage tracing and reuse. So imagine you're running a program and we want to trace the lineage. What kind of operations were executed? Materialize that into an in-memory lineage graph for all live variables, allowing us to serialize this lineage graph into a log file that we can send another user for debugging. So I can tell you a couple of stories where at IBM I spent really all-nighters debugging scenarios where everything was running fine for me, but in actual production environments, people got different results, and we had to debug where all those coming from. And simply being able to materialize such a lineage log file, send it over, and being able to deserialize it, reconstruct the lineage graph, and then reconstruct a program that, given the same input, exactly recomputes the same intermediate, would have been super useful, but was not available back in the days. So we started with being able to debug things, but then the second observation is if we can reconstruct just from the information in the lineage graph an exact intermediate, we can also use the lineage itself as a key in a reuse cache to recycle intermediates that we already computed in large, complex, data-centric ML pipelines. So as one example, on the right-hand side, you see a simple grid search hyperparameter tuning of a linear regression model that takes different lambda parameters. Now, the optimizing compiler opens this black box, and what you see there is that the core matrix multiplies in this closed form regression model are actually independent of the regularization parameter lambda that we feed in there. So those operations can be seamlessly under the covers be reused while producing exactly the same results. Earlier, I was talking about this stepwise forward selection as a means of feature selection. In this case, we essentially, in the previous iteration, already computed an exact intermediate, but now run what-if analysis of appending individual features. So we also support partial reuse, where we reuse a feature and only compute compensations for those additional features. And together, this allows us to eliminate unnecessary operational redundancy, where people enumerate different things in those outer loops, but internally, there's actually a lot of unnecessary computation that's taking place. And this unnecessary computation, as we compose those hierarchical primitives, become inevitable because nobody's changing library functions just to avoid and pull out certain operations. They're just reusing existing libraries. The third example of exploiting redundancy is our work on compressed linear algebra, where we are applying lightweight database compression techniques to numeric matrices and execute linear algebra operations directly in the compressed domain. So a simple example here, so we have an uncompressed matrix, and in compressed representation, this DDC, for example, stands for dense dictionary coding, where we obtain the distinct items in a column, encode then the item as the position in the dictionary. So if the number of distinct items is very small, you get very good compression. Furthermore, we are performing co-coding. So in this DDC case, we co-coded the first and the third column. Here, if there's a lot of correlation, then this does not increase the number of distinct tuples substantially, but we are able to reduce the number of floating point operations because we can perform pre-aggregation on the dictionary. So doing little matrix vector multiplies just on the dictionary, getting one scalar per distinct item that we at the right positions add to the output for matrix vector multiply, for example. Now, in this compressed linear algebra extended, which has been accepted for Sigma 23, we go one step further and now compress in a workload-aware manner by parsing the entire user script that our compiler fully understands. We see what kind of operations are actually executed, and then select the compression scheme, not just to optimize compression ratio. Compression ratio is just a means of making things faster. So if your data set comfortably fits into memory, you should err on the side of making the operations faster. If your data set is a large distributed data set that even does not fit in aggregated memory, so in every iteration you have to read it from serialized partitions, there you should aim for higher compression ratios. So we are essentially compressing in a workload-aware manner. Once we have compressed this representation, vice versa, we are doing execution planning. Should we run this operation locally or in a distributed manner, according to how good we were able to actually compress our input matrices and intermediates. And current work, we also try to push this compression already into the feature transformations, which have a lot of potential for much faster compression while getting even higher compression ratios. Now, those were examples of automating data-centric ML pipelines, making them faster and scalable. Now, I mentioned that we also want to focus on balancing manual control and this form of automation. So in the second part of this talk, I will talk about two projects, Saga for data cleaning pipelines, as well as Sliceline for model debugging. So this Saga framework is actually currently under submission, made it into the revision, and hopefully is going to be accepted soon. The motivation here is that in data science in general, finding, integrating, cleaning relevant data sets is often very time consuming. Although there are existing data validation and error detection and correction algorithms, in practice, data cleaning is still a very manual, unpleasant, and labor-intensive trial and error process. Now, in the context of data-centric ML pipelines, we have one advantage, though, which is that the ML application that we want to optimize for, we can use as an actual signal how good various data cleaning pipelines are. Now, interestingly, and now we, given that characteristic that we have the signal and feedback, we could aim for full automation. So I want to share a particular quote from a talk on model management 2.0 by Phil Bernstein and Sergey Melnik, who had a reflection on the previous 10 years of schema matching. So we believe that we need to learn from other fields like schema matching, entity resolution. And what they say here is that, well, after a decade of work on schema matching, why is it still so labor intensive to develop engineered mappings? To some extent, it's an unavoidable consequence of ambiguity. And then they go on and say, given that the specification of meaning is weak, but the mapping must be precisely engineered, it seems hopeless to fully automate the process anytime soon. So human needs to be in the loop. And we believe a similar scenario is the case in terms of data cleaning. So the following design principles that we came up with was that we want to simplify and automate the mechanical aspects of data cleaning by automatic pipeline enumeration, while being extensible for new types of cleaning primitives and manual refinements, and then really automatically generate the actual execution plans. So whatever is really specific and requires domain understanding, we want to expose, we want to enable users to refine things of the first enumeration step, while then helping to automatically generate efficient execution plans in a lossless manner according to the specification. So as the one slide overview, what we're doing in Saga is we build a robust library of data cleaning primitives, all implemented in linear algebra, and then introduce algorithms for enumerating DAGs of cleaning primitives and automatically optimizing the hyperparameters. So what also is cleaning primitives, some of you, so we might take additional user input in terms of rules, such as functional dependencies. And there are cleaning primitives such as cleaning by robust functional dependencies. So functional dependency from university to country would be given if whenever we see theocrats, it always maps to Austria. Now, due to data quality issues, that might not be the case because there might be some errors. So robust functional dependencies introduce a threshold and say, okay, if the agreement is true in more than 90% of the cases or 50% of the cases here, then we assume there's a functional dependency, and we can use then this functional dependency to clean the remaining instances that actually violate it and take the majority class and replace here Germany with Austria. Other cleaning primitives that we support is MICE. So MICE stands for multivariate imputation by chained equations. And what it does is if you have those null values, then casting the imputation as a machine learning problem itself. So if you have categorical columns, it becomes classification. If it's a numerical column, it becomes regression. We extract a column, take the existing data set, the existing values as the training set of all the other columns that we have, and this extracted column as the labels. We train a model, and then we use that model to impute the non-existing values. And we do that in an iterative procedure where we impute and we go over all the columns that have missing values in them. And then at one point, we reach a fixed point. So what we are doing, we take our input data set and a target machine learning application, then we enumerate logical cleaning pipelines. Those are the general primitives without tuned hyperparameters. And from the well-performing logical pipelines, really do hyperparameter tuning and come up with physical pipelines with a concrete parameterization of those cleaning primitives and execute them in a data and task parallel way. In order to yield the top K cleaning pipelines that a user can then take and manually refine. Does it make sense? Is that overfitting the validation data set? Should I remove certain primitives? But it's really coming up with the first cleaning pipeline that can then be modified and deployed into practice. So just a little bit more. So we currently support there's roughly 25 cleaning primitives that have a number of parameters. And one interesting observation is that some of those parameters are monotonic. So as one example, let's use this primitive outlier removal by the interquartile range, so IQR. What it does is we compute the quantiles, take the first and third quantile, that gives a range, the interquartile range, and we multiply a k-parameter, often 1.5 or 2, that stretches this range. And then we declare everything outside that range as an outlier and remove them either by the boundary values or completely drop the tuple. Now, what monotonic means is if for a certain, so we want to tune the hyperparameter k, so what is for this application actually the best, at a certain k, no more values are actually removed at outliers. And it has a monotonic property. If from that point onward, we further increase k, we still will not remove any values because the previous value already did not do that. So we can avoid evaluating that and all other combinations of parameters. So this allows us to prune an entire subspace in the parameter range. So there are a couple of those parameters. And what you see on the left is it is meaningful. It's not an order of magnitude, but up to about a 2x number of enumerated pipelines we can get rid of because we know they will not yield different results. So MP is with this monotonic pruning, and SMP stands for sorted monotonic pruning. So if you notice that there's this monotonic characteristic, you might actually want to specifically order the hyperparameter combinations that you're evaluating to maximize the space that you can completely prune away. All right, a couple of experiments. So we ran in this hybrid setup here where we have a scale-up node that's kind of 3/4 of a terabyte of RAM and 112 cores, and a scale-out cluster for distributed experiments. A couple of data sets that are commonly used in data cleaning from both classification and regression. And you see here the sturdy score, and I will show it on the next slide again. So here in those experiments, you see pretty much the accuracy for train and test for the different data sets. For the dirty score, then baseline heuristics, or what the data scientists would do, a very simple missing value imputation, very simple outlier removal strategy, and fixed for all the different data sets. It's a common good heuristic to start with. And then a number of baselines, so BoostClean, HoloClean, Raha and Baran, and our Saga framework. And what we can see is that the basic heuristics, well, they work reasonably well, but there are cases where they are ineffective, so not improving. So cancer, for example, don't improve much from those 45% accuracy. And there are scenarios where it even makes things worse. So the Titanic data set, for example, where it goes down from 76% test accuracy to 70%. For the baselines, we see actually mixed results. There are cases where they significantly improve accuracy. There are cases where they time out, they run out of memory, or they even make things worse. Versus for Saga, we actually see, and this is because many of those frameworks, including Raha and Baran, they are trying to clean the data without awareness of the ML target application. So this is really a case for, by utilizing this more specialized setting and the signal we get from it, we can do much better. And what we show in the Saga framework, that we see very robust accuracy improvements by automatically tuning those data cleaning pipelines. Furthermore, we also took this now, the so-called food inspection dataset. We use the Jenga library to inject synthetic errors and systematically vary the fraction of those synthetic errors. And so this is not in percent, so this is actually 20, 30, 40%. And what we see is the target accuracy, then as we introduce more errors, accuracy goes down, but Saga, so our top K cleaning, the blue line, actually consistently recovers it. We also compared against AutoML tools where, so AutoSKLearn is really production ready. AutoSKLearn 2 is still marked as experimental. So what we see here, we give different budgets, 100 and 200 minutes. On the left, just the dirty data. On the right, you see the data created by applying Saga's cleaning pipelines after automatic optimization. And what we see is that there are multiple scenarios where by multiple percent points, you can improve accuracy, because many of those AutoML frameworks do not yet include data cleaning primitives. Furthermore, Saga, even with very simple linear models, comes very close to the accuracy, even after running AutoML for 200 minutes, considering dozens of different algorithms. So the case here is that with data cleaning, you construct a high-quality input data set, which is almost as important as a very expensive model selection on top that considers a lot of complex models. You can get away with simpler models and just a clean data set. In terms of runtime comparison, Saga also shows pretty, so this is now just single node environment, and we see that compared to more sophisticated frameworks like Baran, that we get substantial reductions in execution time while being able to compute much better accuracy. Saga is also the first framework that actually allows data cleaning or enumeration of data cleaning pipelines in a distributed environment. So in the diagram on the left, we run with different configurations. Specifically, F stands for flattened parallelism, parallel for loops running in a distributed environment where we essentially run multiple pipelines concurrently on the cluster. And this was a 6-node cluster, 32 cores each, so maximum degree of parallelism was 196. And we are happy to see a speed up compared to single-threaded execution of 189, which is very close to the actual degree of parallelism. Furthermore, we scaled the datasets to up to 150 gigabytes to show how distributed data parallel operations perform for those different pipelines. Here, of course, the execution times are much higher, but it's still possible to run those data cleaning pipelines based on linear algebra in a distributed manner in a reasonable amount of time. This was the project number 1, and the last 10 minutes I want to use for Sliceline, which is a form of model debugging. I already heard that you already in this talk series here covered a couple of things on explainable AI and model debugging in general. So the same motivation here. Typical data science scenario is really dealing with open-ended questions, underspecified objectives. So we train certain models, get 85% accuracy, and then have to ask ourselves, is it good? What other properties of the model are there? Is it fair? Pardon me. Potential errors come from many, many different sides. So again, data quality issues, data errors, a lack of generalization, or just intrinsic bias coming from selection bias, how we conducted our experiments, and data acquisition process, confirmation bias when we modified actually via data cleaning pipelines that can introduce bias if a person dealing and overseeing those data cleaning pipelines has certain beliefs and then changes things, and in general missing fairness. The unfortunate problem is that many of those anomalies are silent but can create severe problems. And I think you might be aware with some of those examples of race-biased assessment of risk factors. Another example was Lyme, where the classification of huskies, if you actually look at the explanations, you see, oh, this was just based on snow cover, not on actual properties of the husky or wolf. And in the middle, you see a very famous data set on horses, where the ML community actually conducted incrementally improved accuracy until some explainable AI technique actually found that most of those existing systems that actually appeared in real research papers focused on the watermarks of the input data set because they all came from the same source. And once they artificially removed those watermarks, they've seen that the comparison of different algorithms completely changed. Some were more robust, actually looking at features of the horses, others completely focused just on those watermarks. All right, so what we are doing in Sliceline is we want to find the top K worst slices where a trained model performs significantly worse than on average. So think of it, on average, we have 85% accuracy. Now we want to find slices as conjunctions of attributes, so gender, female, and degree PhD, where the model significantly underperforms. So let's say for this slice, gender, female, degree PhD, we only have 55% accuracy, potentially because this slice is underrepresented. We should go ahead and acquire more data for this particular group, or otherwise improve via constraints the model that we have. So what we introduced here is a very intuitive scoring function that is actually very simple. So E stands for the error, the cardinality of X and S stands for the size of the data set and the size of a slice. So what we want to balance here is the slice error with the slice size. So this scoring function has a couple of very compelling properties. So for this scaling factor alpha, if it's set to 0.5, the importance of slice sizes is equivalent to the slice errors. If a slice is twice as large and has essentially half the error, they get the exact same score. If all the weight is on the slice sizes, then no data set smaller than X can yield a score of larger than 0. The score of the original data set is 0, so any positive score is actually higher error or indicative for higher error. Now, what we then do, similar to this pruning by monotonicity, we try to exactly enumerate the entire lattice of all the conjunctions of attributes. This is, of course, exponentially large, but by pruning with a very simple trick known from frequent item set mining, where a frequent item set, so A, B, and C, can only be frequent if all its subsets are also frequent, so AB and BC and so on. That is not the case. You can prune a node and all reachable nodes from it. And we express that in linear algebra efficiently, allowing us in a single matrix multiply to enumerate with pruning an entire lattice level. And then you go down and you have those coarse matrix multiplies, allowing us to do hardware acceleration and apply the entire host of optimizations we have for operator fusion, for compression, automatically, and distributed execution in this context. So I would skip over a couple of those details because I'm running a bit short of time, but we can do the pair construction essentially via self-matrix multiplies very efficiently. The slice evaluation is literally, you have, and I should use that example, here we have two features, a red and a black feature, one hot encoded, and you enumerate via this pair construction the candidate slices you have to evaluate, and then you matrix multiply the candidate slices with the actual one hot encoded data set. That gives you integer counts on the output, indicating how many predicates were actually equivalent. And as we go down the lattice, in the first level, it needs to be one predicate, then two, then three, and so on and so forth. So we simply compare against the lattice level. And from that indicator matrix, we can very efficiently then compute various primitives. So, for example, the slice sizes is a cal sums of this indicator matrix. The slice errors is a vector matrix multiply. So we have an arbitrary model, the errors in predictions, and we element-wise multiply them with the 0-1 matrix, aggregating essentially the errors on the output vector. Yeah? And then again, can run this very efficiently in data and task parallel manner. A few examples just to, again, we ran over a bunch of data sets up to the Criteo. So Criteo is this famous 1 terabyte click-through data set. We used 1 day of it, which was about 200 million rows, and in one hot encoded form, actually 75 million features. So that's kind of a challenge. But we start with a super toy example, salaries, okay, that has like 400 rows. And what we show here is we disable certain pruning strategies. So pruning by parents and score, pruning parent score and sizes, and not performing deduplication. And log scale the number of enumerated slices, and you see by applying all those pruning techniques, we get them down to reasonably few hundreds of slices we have to enumerate, and this also materializes in the end-to-end execution time. If you take a commonly used dataset like adult, we can effectively enumerate the entire lattice in reasonable 40 seconds in this particular case. And you see in the middle of the lattice, of course, the most options, so it kind of goes up and then goes down again. But with pruning, we bring it down to a level where this is very manageable. We also ran on larger datasets, scaling it up. Essentially, here the US Census dataset scaled by a row replication factor of 1 to 10. Row replication is here really interesting because it preserves the exact characteristics of enumerated slices. So the characteristics are the same, just the data size linearly increases, and we see a somewhat linear kind of increase in execution time. And again, on the right-hand side, we also show how with distributed task parallelism, we can really run those scenarios and get a good speed up compared to local multi-threaded operations. Even on Criteo, so this large 200 million by 705 million ultra-sparse matrix, we essentially can enumerate all the way up to the 6th level where it then converges in roughly 40 minutes on a distributed, relatively average cluster. That brings me to the end already. So we were talking about data-centric ML pipelines, and as we hierarchically compose those individual primitives, we have to deal with partial resource, operational, and data redundancy, and optimizing compiler runtime infrastructure is really key in doing so. Balancing automation and control, what we aim for is really trying to automate the mechanical aspects that unnecessarily require time by users, while providing the right abstractions and integration hooks where people can then fine-tune those individual pipelines and interact with the output that those automatic enumerators actually providing. So it's all about finding those correct abstractions that enable users with control at algorithmic aspects, and then applying lossless techniques of eliminating redundancies under the covers. So I joined TU Berlin in September, and we just reposition the group. So in the next decade, we will work on multiple different aspects, including integrated data analysis pipelines that have really data processing, machine learning, numerical computation, high performance computing. We work on internals for automatic data reorganization, but then also, and that's related to human-centered AI, really data engineering, model debugging that will always be specialized for a particular domain, and then different deployments in data platforms, federated and cloud infrastructures. And I always tell my students, it's very important to interact with use cases and interdisciplinary collaborations for grounding to avoid creating artificial problems. And ultimately, it's about finding the right abstractions for all those different tasks in the end-to-end data science lifecycle. All our systems are open source, and more than happy to take any questions. Thank you very much.
Thank you, Matthias, for introducing the nice work that you did and those systems that you built. Now, time for questions from the audience. So if you have any questions in the audience, please, you can unmute yourself and just ask. Well, maybe while the audience is thinking, I can start with a couple of questions. So, Matthias, thanks again for presenting the Sangha and the slide work, right? So while I was listening to your talk, because I do human in the loop, human-centered AI, this kind of topics, right? So I constantly have this question in mind. For example, in the data cleaning work that you did, you used outlier detection, I mean, some automatic method to identify the potentially problematic entries in the in the database. So what if, let's say, for example, if there is some structural noise that those problematic entries, that it doesn't appear as outlier, but rather, that they come in groups with certain with specific features, right? That it might be hard to see what's going, or if or not there's anything going wrong there.
That's a very good point. So there are multiple different strategies for outlier removal. So the very simple strategies I showed was point outliers. But indeed, for time series specifically, there are sequence outliers where the individual points are not problematic at all, but because they appear in the sequence all a little bit lower than the average or the typical fluctuation, they are problematic. So we have a couple of additional primitives that we did not include in this particular group, specifically for time series. So what we are using our matrix profile. It's very successful work that's very simple, and for that we also integrated it, which is if you have a time series, you chop it up into a certain sequence length, so windows, and then you simply compute the distance of every sequence to all the other sequences. And this is a nice anytime algorithm, so you don't have to materialize all that, but just for every sequence you keep the max distance, and you can sample that, or if you have enough parallelism, nicely distribute that. And ultimately you want to obtain as the outlier then the sequence that has the largest distance to all the other pairs. Sometimes in existing group, they are called the cohorts. So the points that are that have the largest distance to any other points and are somewhat isolated with that. But you're absolutely right. There are different strategies, and in this particular work, we did not focus on all of them yet.
Do you think there would be certain cases it's necessary to have humans involved?
Humans involved, and that goes back exactly to the design principles. Exactly for that reason, we said it needs to be extensible for new data cleaning primitives. So the way we envision it, that you have a good idea of a suspicion in your domain, what happens, you write your own primitive, you define the hyperparameters, and if they are monitoring or not, they are registered. Simply, in our case, it's a data frame that is handed over to the actual pipeline enumeration, and all the mechanic stuff is then happening still automatically. And you get a pipeline out, and then you can say, oh, that pipeline is not very good. I should add another primitive, or should not be as aggressive. So we've seen actually very interesting things where we introduced outlier detection that eliminates certain values. And because it eliminates values, the automatic enumerator also injected a missing value imputation to fix those errors that we have removed. And then we had a data set where only on the test set, there were actually missing values. And then this pipeline is very robust of also capturing those kinds of cases. But you want to see the pipeline, you want to inspect it and see, okay, this is the order, those are the primitives, those are the hyperparameters, and you can modify and craft them. But it's a good starting point for, instead of starting from scratch and trial and error your way to a reasonably good performing pipeline, use a tool that gives an initial set of proposals and then fine tune that. That's kind of our approach to the interaction with the user there.
I see. Cool. So maybe to push this a little bit further. So from your experience, right? I totally agree. Right, there would be a desirable property such that of the system such that it can be, that the humans can refine. Right, it can be improved over time, and it has this interface to the users or developers to allow them to inject new knowledge in terms of how to handle those problematic entries or noises. So my question is, so related to this, so from your experience, how dynamic do you see? Of course, it's a domain dependent, it's data set dependent, task specific, right? But then how maybe from your experience, how often does this get like new primitive, right? How often does that get created or injected into the system?
It's an excellent question, and I go a little bit back. So while working on SystemML, we were very, back at IBM, we were very biased because the team we were working in, we had a couple of people from distributed systems, data management, core ML systems, and then also core machine learning. They were crafting the first algorithm libraries in scripts for us. And there we focused on essentially enabling ML researchers to quickly write new algorithms without worrying about how the execution plans are generated. And after reflecting over that, this was a mistake. This was way too niche, because for every ML researcher that can devise new algorithms, there are 1,000 data scientists that mostly call existing library algorithms and trying to orchestrate and compose them. So in that regard, I would say it is relatively infrequent that specific for a domain, people will introduce new primitives. Usually that happens long in the development process. So having a good library of existing things just to choose from, and what we've seen that people want to experiment with things and play around, and what would the result be, so what if analysis. But having the ability after it's running reasonably well to then later tune it once you have time, because you have something deployed in practice, and you can really focus on getting this better and better. So I think finding the balance between having a library that gives you something good, valuable out of the box, and then having enough time to actually craft domain-specific extensions is the right thing. And it's a longer time scale. So it's nothing that is in a single session. Things people come up with new ideas for new cleaning primitives, because it's always risk of contemplating what the impact on an actual deployment setting will be. So you will not see everything in your exploratory session. And with that, people try to minimize risk, stick to existing algorithms that are trustworthy, and then very slowly improve upon them. And that's at least our current, what we typically see in developing those projects and working with ML applications and use cases.
Yeah, indeed. This would be a longitudinal study, right, where you would need to observe for a long period of time in order to gain some insights. Cool. Thanks, Matthias, for sharing your observations. Do we have a question from the audience?
And it can go in all directions.
Yeah.
We're working in the end-to-end data science lifecycle, so anything.
Thanks for being open-minded. I can actually ask another question. Maybe it's more about clarifying things in work. So in the model debugging work that you did, the slice line, it's a very nice name. So
this is actually taken from an HBO series, Slice Line, or Silicon Valley, and their slice line was a rather stupid idea of buying pizzas and reselling them under a new name. But it nicely came together the linear algebra for the kind of line and slices for what we want to find. Yeah, so it's
well, it also reminded me of this story. I was actually I watched this TV show, right?
Me too.
Valley. Yeah, it was a very nice story. So so in this work, you're assuming that the data comes in the format of a structured way, right? So tables. But then, so I was wondering if you have any plans, to extend this to language or vision tasks where the data is more unstructured.
Definitely. So we exactly want to do that now in joint projects in the medical domain. So prior to the talk, we talked a little bit about that, and that's exactly what we want to do for multimodal input data sets, and combined with reasoning about the data representation that is being fed into neural networks, and potentially thinking about coarse-grained features that people as a pre-processing step construct upfront, and how we get the information from the actual model debugging at the output back to the input, but we don't have any results or concrete ideas yet. But as a goal, definitely interested in it. Yeah.
Yeah, maybe a bit of a shameless advertisement of things that we are doing. So we're actually working on converting, those unstructured data into something more structured, including, for example, interpreting the image pixels, right, to something that is more structure, like concepts with attributes and relationships. And we are doing that for visual data as well as for language data, where potentially what matters not only the words, but also the syntactic relationship between those words.
Yeah,
actually
graphs. Absolutely. So, and I think that's a very good strategy. So, thinking back of work like Snorkel for data programming, what they also did in a couple of, I believe it was the Snooper paper, where they defined a couple of higher level features, like there's a bounding box with at least that dimensions that is a round tissue that's a little darker than the other stuff in order to identify cancer tissue, for example. And then running or writing those labeling heuristic functions on top of those higher level features was very effective for them. So I absolutely believe that this is a good direction to pursue, which is of course very complex. How do we design them automatically and make them generalizable, not just for one application, but for a broader set of applications. Yeah? And I will definitely look up your works in this space. Yeah.
Thanks. I will share with you some of the papers that we have. Cool. Thank you, Matthias. If we don't have any more questions from the audience, I can actually go. And thanks again, Matthias. It's a great pleasure to have you here. And thanks everyone for joining. In 2 weeks, we will have the last talk for TAF from Professor Philippe Kudemaru to introduce the work. So see you in 2 weeks. Thanks again, Matthias.
Thanks for having me. Bye.